I'm working as a PhD student. I'm working on image generation. So what do you do when we do generative model? Usually you want to generate a modality. In my case, it's an image, but it could be applied to many other things like video or sounds or whatever. And what you want to learn is, usually you want to learn and to be able to sample from the image distribution. So what you will do is you will start from a Gaussian distribution, for instance, noise here, and you will learn a mapping, and learn is the model, a mapping from the noise distribution to the data distribution. Just basic about generative models. And if you want to do text to image generation, for instance, or text to video or whatever, you will condition the model by a text, for instance, an image of a parrot in that case. So this is the task that I'm trying to solve. Enfin, not to solve, because actually you may know some models that are already doing this pretty well. So what I will try to do is to improve the efficiency of the training pipeline of those models. So I don't know if you're aware of what is the current recipe for state-of-the-art model in image generation, but it's quite similar to what we do for large language model, if you're aware of that. So usually you start from web scrape data, so a lot of images, billions of images. You do first a big pre-training on this gazillion of data, and then you have a second and a third stage about fine-tuning and alignment through reinforcement learning usually. So that's the basic setup. But you need gazillion of images, many GPU hours. So it's quite heavy. Yeah, quite heavy because of that. So we will try to tackle several aspects of this pipeline to improve the efficiency through this talk. So yeah, I wanted to present 3 papers, but I guess we'll have time for only 2 of them, the 2 best ones maybe. So the first one, we will tackle the data efficiency through a first paper, and then we'll go to the alignment part. So the first work I did during my PhD. So how far can we go with ImageNet for text-to-image generation? So the dataset we use, as I said, are web scrap from internet. For instance, Lion, if you know that. It raises many issues. First, reproducibility. When you do research, not everybody has the same copy of the dataset, because when you download the dataset, it's just the URLs to get the images. Some are taken down. There is also a copyright issue with the dataset. And maybe one last thing is safety. You don't know what you have in this dataset. It can be yeah, many things, copyright, not safe for work images like pedopornography or any kind of images you don't want your model to be trained on. So and there is also the question of the size. For many domains, for instance, in medical images, you are not able to get 5 billion images. So we wanted to reduce the size for those questions, and we choose to use ImageNet. So for those who were doing computer vision like 10 years ago, it's a very well-known dataset that was primarily used for classification. So 1 million images with labels. This is a golden retriever. This is a cat, many classes. So we want to train on this dataset, but the first challenge is that there is no caption to do text to image. So we can train on class label only, but an image of a golden retriever, it's nice for this one, but you lose a lot of information from the image, from the pixels. So the first thing we did was to use VLM to get very long captions from those images. Maybe in 2026, it's not a big trick because everybody is using it, but 2 years ago it was quite a good idea. So yeah, that was the first thing. So if you train a model like this, it will work well. Yet it will overfit very quickly because there is only 1 million images. And also, as ImageNet is object-centric, so it's usually one zoom-in version photo of an object, as this one, the compositional abilities of the model are not very good. So we tried another trick, which was data augmentation. So we tried different strategy. The first one was cut mix. So the object it's very simple. You take 2 images, you downscale one, and you copy paste on top of the other one. It creates fakes, co-occurrences in the data set that the model will learn but that were not initially in the dataset. And the other ones are crop, so you just take a zoom and the model will only see the tokens inside that square, and the crop and resize where you zoom in. This is mainly to tackle the issue of scale within the images. So using those two tricks, we train a model like this, and we compare it. So this is a Generative result, if you know about this benchmark. It's a composition benchmark, and we compare our model trained on ImageNet, so it's a small model, 300 million parameters, to the state-of-the-art, so mainly Stable Diffusion models. And the x-axis is the data seen during the training, and y-axis is the performances. And we see that we are able to match performances better than Stable Diffusion and around Stable Diffusion 3 with only 1 million images, so more than 1,000 times less data. So yeah, some nice images, I believe, and we compare them to other models. So it was nice. This one last goodies about this project, which is very nice, is that ImageNet has been released in 2014 or 2012, something like that. And it was using images collected up to 29. So lots of concepts that are present in the world nowadays were not available in that dataset. So it was a very good setting to test the generalization capacity of the model. So we try, for instance, on the third images, can the model generate an iPad, which was not created when the dataset was created. So the model is somehow able to get an iPad. Maybe it's not the best one, I agree, but still is able to understand the concept that an iPad is maybe in the embedded space between a TV and a phone, and it works like that. Same for, so ImageNet is only natural images, so there is no Phoenix, for instance, inside it. So we are able to generate that kind of images, which was pretty nice. Okay, so this was the first part. So from web-scale data that we don't know, we can go to clean, smaller data. It's a control setup. And then there is the end of the, not the end, but like the rest of the pipeline. So with the three stages, pre-training, fine-tuning, and reinforcement learning. Usually, you do the alignment at the last step, and there you use reward models. So reward models could be very well known, like LeetScore, to you want images that align well with the text. It could be about aesthetics. You want appealing images, or it could be, for instance, physical plausibility. Actually, any kind of reward you want. And usually, the distribution you want to sample at the end of that that stage is very far from the distribution you will get after the pre-training. So it's kind of wasteful to do like this. And also, if you have already trained reinforcement learning, it's the pain to train, it's the pain to make it converge. So we wanted to remove that. Yeah, sorry, I just explained that. So here comes the second work, so MIRO. So and this work has just been accepted at ICML. We presented it a few weeks ago in Seoul. It was very nice. So what we do, we merge those three stages into one training steps. And what can we do? Instead of pre-training an uncurated dataset and then showing the model good images that we want to generate, we will show directly during the pre-training the signal from those rewards. So instead of filtering by rewards and optimizing for those rewards later, we will condition during pre-training on those rewards. In other words, we want to learn the joint distribution of image and the rewards instead of learning the image distribution and then filtering to get to bias the distribution toward one region of the distribution. So what is the training with the MIRO pipeline? It's the basic training. So here is the basic training. You know the image, you ask the model to denoise it. And for each image in the dataset, we will score it with many rewards, any reward you want. Actually, we have taken all the most famous available on Hugging Face. And so you have for each image a vector of scores, and you condition the model on this reward, on this vector of scores, sorry. So this is during training. During inference, we will condition the model with the vector of the highest reward possible to get the best image possible. And for those who are familiar with guidance, we can apply a MIRO guidance, where instead of doing guidance between condition and uncondition, we do guidance between highest reward condition, lowest reward condition. Yeah, 3 goodies about that training pipeline. First, we have a faster training. So on this example, we can see that with around 75K steps of training, we have already good images, whereas the baseline takes much longer to get nice images. We have another example there with the tiger. With 50K steps of training, we already a good image, whereas the last one from the model, from the baseline. Yeah. One other thing is that as we optimize, we are not optimizing, but as we condition on many different rewards, the model is able to learn the full joint distribution, and we are Pareto optimal on all the rewards. This is what we can see on this spider plot. Another good thing is that if you look at the aesthetic one, so we compare the model trained conditioning on all the rewards with model trained condition on only one reward. And we can see that the model trained only with aesthetic reward is pretty good at aesthetics, but very bad at all the other rewards. This is what we call reward hacking, and it's a very big problem in reinforcement learning. With MIRO, you're able to manage the tissue and have something that is good at both rewards without impacting the others. And one last thing is that at inference, for the end user, you have controllability. So I said that during inference, you use the reward with the higher scores, but actually you can use any vector you want to condition the generation. So if you want to balance some reward that are not that useful or that for a very specific task, you can do that, which is not possible with reinforcement learning. Once you have biased the distribution, you cannot go backward. Yes, and if we compare against the state of the art. So the first plot is the general score as the previous one. And we see that the 2 orange models, so it's MIRO and MIRO with test time scaling, but I will not talk about that. It's able to beat, so it's hard to read the label, but it's able to beat Flux, so a big commercial model, the open version of Flux. And the 2 plots below are about the size of the model. So we have a pretty small model compared to Flux, which is the last one. So 400 million parameters compared to 12 billion parameters. And on the right one is the inference cost in flops. So yeah, with a very small model, very efficient to run, we are able to get very strong results. I don't know what time is it, if I'm running short in time. But maybe one last thing to finish. What if we merge both together? So we tried to train a model on ImageNet only. So yeah, just to be clear, the MIRO model was trained on more data. It was trained on CC and yeah, on 20 million images. So it was a bigger model. But we tried to merge both. So we score all the ImageNet images, and we are able to increase a bit the performances. And now we are ahead of Stable Diffusion 3. So the last Stable Diffusion model, and it's not on that plot, but we are 2 points below Flux with only 1 million images, which was pretty nice. Yeah, and I think I will stop here. I don't know the time, but thank you.